Right, so there we go. There. Right, well, good morning and welcome to this webinar. As Stephen said, what we're going to talk about today is really about garbage collection. I've called it the future of garbage collection in Java. And the reason for that is that if you think about it, JDK 9 is now only a few months from launch. And there will be a couple of changes that are happening in terms of the way that garbage collection works when we look at the Open JDK project and how that filters through into the way that Java supports that. So what we're going to do is talk about those changes and also talk a little bit about the sort of future of garbage collection in terms of what's going on beyond that, what people are thinking about, but also talking about what's happening today and how we can address the needs of garbage collection today. So what we need to do is to start with just a little bit of a recap and a little revision so we understand why garbage collection is important. What's the purpose of garbage collection? How does it work in terms of the fundamental principles? So let's look a little bit at the idea of Java and memory management. Now, if we think about it, this has been a problem that has always affected computer science. When we want to write applications, we need to store information. We need data, we need objects, we need values to make our application work. And in order to do that efficiently, what we need to do is to be able to allocate the space from the memory in the computer to enable us to store that data. But because we don't have an infinite amount of storage in our computer, we also need to have some way of reclaiming that space when we no longer need it. The most important thing is how do we do that reliably? How do we do it efficiently? Different languages have taken different approaches to the way that we do that. If you look at C, there is malloc and free as library calls. What that will do is it will allocate you an area of memory, it will return a memory address that you can use to store data, to manipulate, but you have to remember that when you've finished with that area of memory, that you must explicitly call free with the correct address. This is one of the things that can be a little bit of a problem. Either you forget to call free when you should do, and you get a traditional memory leak, or you may call free with an incorrect address, and you're trying to free memory that you don't actually have reference to, which can also cause problems and your application stops abruptly. C++ is object-oriented and takes a slightly different approach. So you can instantiate objects using new, you get a pointer to your object, but again, you must explicitly tell the system when you finish with them. So you have to remember to delete your objects when they're no longer required. Java takes, again, a slightly different approach. It's object-oriented, so in the same way that C++ instantiates objects, Java does the same thing. You request a new instance of an object, whether it's a string, whether it's a list, whatever. But you then don't have to worry about remembering to free it up. You don't have to remember to tell the system that you no longer require it. JVM will track everything for you and will decide when that object is no longer being used and can then reclaim the space at some point so that it can be reused for another object. Now, again, thinking about a little bit more detail of Java memory management, Java doesn't use explicit pointers. In C and C++ and languages like that, you actually have a memory address that points to an area in virtual memory that you can then store data in. You can also use that as a number and you can manipulate it by adding something to it or subtracting something from it. That can cause problems because very typically, if people are trying to break into your system and cause security problems, they can use things called buffer overruns where they say, okay, I know where this buffer begins. I can then address something beyond the end of that buffer and gain access to memory that I shouldn't have access to. Java doesn't have that. So you can't manipulate pointers in the same way. You can't simply add a number to a value of a pointer to an object and be able to change what it points to. That just doesn't work in Java. We have implicit pointers to objects, and it's very safe from the point of view of not making mistakes, not letting people do things that they shouldn't do with your code. The JVM handles all of the memory management for you. When you want to create a new object, you don't have to request an area of memory. The JVM will do that for you. You simply say, I want a new string. The string is this size, and the JVM will allocate enough space for you to store that string or that list or whatever on the heap. When those objects are no longer required, it's up to the JVM to figure out how to locate those objects and then how to reclaim the space that's been used by those objects so that it can be used again to store new objects. In terms of the way that's specified, if you look at the JVM specification, which is part of the Java SE specification, it says that there must be a garbage collector in the JVM. There's a system.gc call, and that says that if you call that method, at some point in the future, garbage collection will happen. But it doesn't actually say when. It simply says that at some point in the future it will happen. And this is quite important because although garbage collection is specified as part of the Java virtual machine, how garbage collection is implemented is not specified. So the way that it actually works is left up to whoever develops their JVM. You can do that in whatever way you like, whatever way is most appropriate, as we'll see as we go through with some of the examples. So in theory, this sounds quite simple. All we have to do is let the JVM do its work, and from an application point of view, we simply concentrate on saying, okay, we allocate these objects, and then at some point the garbage collector will reclaim the space and everything will work very nicely. Unfortunately, as I'm sure you know, the reality is a little bit more complicated than that, and that's really the reason why I'm talking about garbage collection today. People have a number of misconceptions about garbage collection, so let's talk about some of those. The first is that they often can be a little bit negative about garbage collection. The reality is that it's better than you think. Garbage collection in the very early versions of Java was very basic. It didn't really take advantage of the hardware. It worked in a very simplistic way, which meant that you would have long pauses associated with even the most basic of applications. Many people in the early days of Java started to think of Java as slow because of the impact of things like garbage collection. We've had 25 years of development of the virtual machine since it first started being developed, and a lot of work has gone into making garbage collection work in a better way. So what you find now is that garbage collection is extremely efficient. Algorithms that are being used internally are much, much better than they were in the early versions of Java. In terms of collecting dead objects, the overhead of actually collecting them is either nothing or very low. If you look at the young generation, when you need to do a minor garbage collection, which is moving any live data from the young generation into either the survivor spaces or the old generation, you simply ignore dead objects. So you don't actually do anything with them. You simply ignore them, and then you reset the young generation, the Eden space, so that it can be used again for new objects. It's only the live data that needs to be copied. Only live data is going to impact in terms of how long it takes to do the garbage collection. Garbage collection will find all of your dead objects. Even if you have cyclic references, two objects that refer to each other, 3, 4, 5, doesn't matter how big the cycle is, the garbage collector will understand that even though these objects have references to them, none of those object references are coming from your application code, and therefore it will be able to reclaim all of the space for any objects that are no longer referenced by your application. That's the good news. The other side of it is that it's sometimes worse than you think. And what you'll find is that if the garbage collector, especially with the old generation, has to do a full compacting collection, and that's what happens with every garbage collector that you'll see except for Xing, which we'll talk about a little bit later on, it will take roughly 1 second per live gigabyte of data to do that. And in fact, the pauses that you'll have for the old generation will be proportional to the size of the heap, not to the size of the live data. So there's a lot of work that needs to go on to do that. Garbage collection does not prevent memory leaks. I mentioned memory leaks in terms of forgetting to free objects or forgetting to free memory using malloc and free. That's your traditional type of memory leak. But in Java, you can still have memory leaks. Even though the garbage collector is very good at locating and identifying data where it's no longer required, if you maintain a reference to it from your application code, the garbage collector has no way of knowing that that object is no longer referenced and is no longer used. So if you maintain a reference, it will not be garbage collected. And that means you can have memory leaks in Java applications because of the way that you write your code. The other thing that people often do is that they try to tune garbage collection to eliminate the problem for a certain length of time. And what they try to do is they try to push any significant pause for garbage collection beyond a certain point in time. So they'll say, right, we ran our application for 20 minutes and we didn't get any significant garbage collection pauses, therefore we finished tuning. Problem is, your application may well run for an hour, it may well run for a day or a week, and the chances are that even with a very large heap space, you're going to get to a point where you will see significant pauses in your garbage collection. All you're doing is pushing the problem further and further away. What you need is a better solution to that, which we'll talk about later. Other misconceptions that people have. Often people look at garbage collection in a slightly negative way, and they think that if the garbage collector wasn't there, that all their performance problems would be solved. Because of its non-deterministic nature, people sometimes don't like the idea of the garbage collector, and they think that if they could take control of the way that things worked, then they could actually solve the problems they have with performance. The reality is that the JVM saves you a whole lot of work in terms of your code. So you're not having to do explicit memory allocation, you're not having to do tracking of your own memory references and your own objects, and then having to free those things up. People often say to me, oh, wouldn't it be great if we could use malloc directly in our Java code? If I could allocate some space, then I could put my objects in there and I could, make that work better. Again, the reality is that Java's way of allocating space is actually much quicker than using malloc. Malloc has to go down into the kernel, it has to use the virtual memory system, and it has to find an area of memory that's big enough for what you want to store. That takes time, there's lots of code involved. With Java, the Eden space, which is where most objects are allocated initially, it's only if they're very large they won't be allocated initially in the young generation. The way that works is by using a stack-based allocation. What that means is that you have a pointer into your Eden space, and that's where the next object is going to be allocated. When you want to allocate an object, all the system has to do is move that pointer by the size of the object, and it's ready to allocate another object. You then get the pointer where the pointer was. That takes about 6 instructions, so it's very, very quick to allocate a new object in Java. Other things that people do is they say, well, how about if I just eliminate all of the garbage from my application? Garbage collector is causing me problems. Why don't I stop creating garbage in my application, and then the garbage collector won't have to do any work, and my performance will be massively improved? Well, yeah, you can do that. The reality is, though, you will spend a lot of time trying to rework your code. You will focus on things which are not the problem you're trying to solve. You will be trying to solve the problem of not generating objects, not generating garbage, rather than solving the business logic issue that you need your application to deal with. You're simply trying to eliminate object creation. People often, to do that, use object pooling. And object pooling, from an advice point of view, is that unless you're using heavyweight objects that take a long time to create, a long time to tear down, things like threads, things like SQL connections, then object pooling is a waste of time. Having an object pool of strings, having an object pool of integers doesn't make any difference. The garbage collector is really good at what it does, and trying to build your own virtual memory system on top of the virtual memory system of the GC, which sits on top of the virtual memory system of the underlying operating system, just isn't going to give you any great performance improvement. There are probably one or two very, very extreme situations where this might make sense, but for average general applications, unless you're using heavyweight objects, do not bother with object pooling. It just won't help you in terms of performance. Right, so that's the idea of memory management in Java. Let's look at some of the garbage collection fundamentals in the Java environment. Now, first thing is concurrent and parallel. These are two terms which are used, and people often get a little bit confused about what they really mean, especially in terms of garbage collection. Now, concurrent actually means parallel as well. So what we're talking about here is that you have the garbage collector, which may have a thread or threads running to do its work. You also have your application that has threads doing its work. When we talk about concurrent, we mean that the garbage collection can run at the same time as your application threads. So the garbage collection is doing its work as the application threads are doing their work. Parallel is the situation where you have multiple threads for a particular task. So you could have multiple threads doing garbage collection, so they'll be working in parallel. You could have multiple threads doing the work of the application, running in parallel. Those sets of threads running in parallel can then run concurrently where the garbage collection and the application threads are doing their work at the same time. So concurrent and parallel are similar but distinct in terms of what they mean from the point of view of garbage collection. We also have the idea of what are called conservative collectors and precise collectors. Conservative collectors are ones where not necessarily all of the object references are tracked by the virtual memory system. It will keep track of most of them, but there may be some, because of strange things, circular references is a good example, where it may be that the garbage collector is not necessarily completely sure whether a field is still referenced or not. The opposite of that is a precise collector, where absolutely everything is tracked. The garbage collector, the virtual machine, is aware of all the references from the application code to all of the objects in the heap and which ones no longer have references to them. If you look at all the commercial collectors out there, they will all be precise. It makes a lot of sense, because if you don't have the knowledge about where all of the objects are and where all of the references to those objects are, then you cannot possibly move objects around within the heap. You need to be able to move objects around within the heap in order to compact and eliminate fragmentation. If you've got gaps between objects and you want to eliminate those, you have to be able to move objects around. Only way you can do that reliably is by using a precise collector. If you didn't have a precise collector and you started moving an object around, it could be that you would move an object and copy it over another object that's still being used. But because the collector didn't know about that reference, it didn't know that it couldn't move an object to that place. So you must have a precise collector in order to do moving, and in order to do that, we use that for all commercial collectors. Right, so let's now look at the state of garbage collection as it is today. So this is up to JDK 8, which is the current release of Java. Realistically, you can look at 3 different versions of Java, different providers of Java runtimes, Java development kits. So Oracle have what they refer to as their hotspot virtual machine, Azure have Xing, and IBM have J9. And all of those, with the exception of Xing, have different versions of the collector available. That allows you to tune things so that you can take care of different situations depending on how you want the garbage collector to work. Why Azure Xing only has one collector, I will explain a bit later on, because you only need one collector for all situations. In terms of hotspot, up until JDK 8, the parallel collector has been the default. There has been a concurrent mark sweep collector as well since Java SE 6, in fact probably before Java SE 6. And then in Java SE 8, we saw the G1 collector introduced as a production-ready version of a collector. G1 had been around for a while before that, but it had only been as an experimental option, and it wasn't recommended for production systems. As I said, Azure Xing only has one collector, that's all we need. IBM J9 has some slightly different versions which are related in terms of the algorithms. So there's opt throughput, which is a mark sweep algorithm that runs on a flat heap structure. There's GenCon, which is a generational concurrent collector. That's the more recently has been the default for IBM J9. And then there's the balanced collector, which is a more recent introduction for them, which is, again, trying to balance the idea of throughput versus latency and using an incremental approach to try and drive that in a better way. If we look at OpenJDK, which is the source code base for the reference implementation of the Java SE standard, we will find that there are a number of collectors available, and you can choose which one you want to use depending on the situation that you have for your code. The oldest of those is the serial collector. It's the least sophisticated. It uses a single thread, as you would expect, for collecting both the young and the old generations. In terms of the old generation, it uses, again, a fairly simple algorithm. It's mark, sweep, compact, which means that it has to pause all of the application threads while it does that work, because it's moving objects around, and if the application threads were still running, they may be updating objects as they're being moved, and you could get inconsistent data because the changes that are being made in the wrong place or not replicated in the right place. So you get significant pauses with that because, again, it is a serial collector and only one thread is able to do that work at a time. To maximize throughput, the parallel collector was introduced. And the idea there is, again, as the name would suggest, that you use multiple threads to do the work of the garbage collector. Again, this does compaction in the old generation, so you do get pauses for the application threads, but it's designed where what you're looking for is to get the biggest percentage of time to run your application threads versus garbage collector. If you're doing something like batch processing where you're not concerned about the individual pauses and the sort of latency that the application has, but you are concerned with how long it takes to finish the job completely, then the parallel collector works best in that sort of situation. That is the default collector for what are called server class machines in JDK 8. Server class machine is defined as one that has 2 or more cores, processors, 2 or more gigabytes of memory. A slightly more modern collector that was introduced is the concurrent mark sweep collector. This is also called the low pause or the low latency collector. What this does is to run concurrently. This is a situation where we can see the garbage collection threads doing some of their work at the same time that application threads are doing their work. How that works is that you have an initial marking phase where the garbage collector will pause the application threads. It will mark all of the immediately accessible objects that the application threads have. It will then restart the application threads and allow them to continue doing their work. At the same time, the garbage collection threads will follow the references from the root set, as it's called, and build up a graph of all the live data from that root set. So it will follow all the links from objects to other objects that you have within your application. When that's finished, it has to do another pause of the application threads so that it can check any changes that have been made whilst that concurrent part was going on. At that point, it has a full picture of what is live data and what is garbage, and it can use free lists to maintain the gaps between those live objects and allocate new objects in those spaces. So it doesn't do compaction as the application threads are running. The thing is that with the CMS collector, at some point, you'll get significant fragmentation, you'll run out of the ability to find spaces between live objects, and you will have to do a full stop-the-world compacting collection. That would give you potentially a long pause with your application threads. G1 is the most modern collector in the OpenJDK, is referred to as the garbage first collector. It's very similar to the concurrent mark sweep in that it uses the same basic algorithm, but it also is able to compact some of the data concurrently. I'll talk about that on the next slide. However, even though it does do some compaction concurrently, it still has a situation where it can fall back to a full compacting collection. So again, you will potentially have long pauses in your application threads as that compaction has to take place and objects are moved around. The idea behind this and the design is to make your garbage collection more predictable in terms of the types of pauses and the length of pauses that you get. And it's also designed to work with slightly bigger heaps. So it's designed for 4 gigabytes or more. If we look at the heap layout, this is the thing that you would see in terms of the concurrent mark sweep. The heap is divided into generations, so the top part where you see the green areas, this is the young generation. The young generation consists of the Eden space and 2 survivor spaces. Survivor spaces are designed to allow objects to stay in the young generation a little bit longer, with the idea that they might become garbage before they get promoted into the old generation. Really, you want your objects to be as short-lived as possible and to die before they leave the young generation. If they do make it into the old generation, which is the area with all the blue parts in it, what we see there are blue areas representing live data and the grey areas representing the gaps between them, which is where new objects can be copied to. Space can be allocated for them in the old generation. As you can see, you can get a lot of fragmentation. You can get lots of small gaps between objects and objects spread around throughout the heap. The key thing about this is the whole heap space is one big area. It is contiguous in memory and is designed in that way. If we look at G1, what G1 does is it takes that same heap space and it breaks it up into regions. These regions then are put together to build a logical area which can be referred to as the young generation or the old generation. Unlike in CMS where you have contiguous areas of memory, in G1 what you're doing is taking a number of regions, linking them together and making that a logical old generation or a logical young generation. Regions are not tied to a generation, so when a region is no longer required for one region, it can be used for another region. Now, looking at the G1 collector in a little bit more detail, from the young generation point of view, the same approach is taken to other collectors, where you have, in effect, an area of memory, which is a number of linked regions, and you have a pointer into those regions which moves along as you allocate objects. When you get to the end of that logical region, you need to do a minor garbage collection, and at that point any live data will be collected from those regions and copied into survivor spaces and then promoted into the old generation. The old generation uses a similar idea to the concurrent mark sweep. So it does an initial marking phase, it does a root region scanning, then it does the concurrent marking phase so application threads are able to actually run at the same time. It then has to pause application threads again, do the remarking to catch up with any changes that the application threads have made during that time, and then it does some cleanup. But it is able to compact at the same time. Now, looking at the regions that are used within the G1 collector and G1 heap space, what we see is that those regions can be from 1 to 32 megabytes in size. That really depends on the size of the heap that you're using. The bigger the heap, the bigger the regions are going to be. What typically happens is that the heap space that's available gets divided up into 2048 regions. And depending on how big your heap is, those 2048 regions will be sized accordingly. G1 also has the idea of what they describe as humongous objects, objects that are more than half a region in size. If an object is more than half a region in size, then it will be allocated directly into the old generation. It won't go through the young generation. By breaking things up into regions, what this means is that the way that the collection works is that compaction can happen in an optimized way. And what I mean by that is that when the heap is being collected, the old generation is being collected through the concurrent mark sweep idea, the regions can then be sorted based on how much garbage they have in them. And you start with ones which are potentially completely full of garbage. If they're completely full of garbage, there's no live data in those regions at all, then it's very easy to reclaim them because we know that it's all garbage, so we simply say, right, just treat that as an empty region, put it on the list of regions that we have available, and it's automatically collected. So then we're able to reuse that space immediately. If we have a region that has mostly garbage in it and only has a very small amount of live data, then those regions can be garbage collected and compacted very efficiently. So if you had, let's say, 10 regions which only had 10% of the available space occupied by live data, you could take those 10 regions and compact them into one region. That frees up 10 regions. You're only using one region to store that data. It's very efficient because you only have to copy a small amount of data from each region. You're getting a large number of regions back in terms of that compaction. So the collector will gradually work down the list in terms of seeing how much data needs to be copied. At the bottom of that list, where you've got regions that have a very large percentage of live data still in them, it may be that it doesn't make any sense to copy that data and collect the and to compact the data, because what you're going to get back is a very small amount of space in that region. So in that case, some garbage may be left behind, and the next collection, or maybe even later, will be when that garbage actually gets collected and compacted. So the way that the G1 collector works is that for every run of the garbage collector, it may not collect all of the garbage, but that's only from the point of view of performance. It doesn't mean that garbage will be left behind indefinitely. It's only if it needs to be done for performance reasons. The garbage collector will still track all the references and will still know what is garbage and what is live data. Now, if we look at the immediate future of garbage collection, what we're dealing with is what's going to happen in JDK 9. There are a couple of changes happening here. So the first of those is that the default collector is no longer going to be the parallel collector. In JDK 9, G1, garbage first, will be the default collector. This has been defined through JDK Enhancement Proposal, or JEP 248. The reason for this is that the G1 collector is more tuned for lower latency rather than throughput. And people tend to prefer applications to run with lower latency rather than higher throughput. Most people are looking for response time for an application rather than batch processing times. The other thing is that G1 has been around for a long time. In fact, the initial work on G1 was a paper that was published back in 2004, so it's well over 10 years old now. And it means that the development of G1 has become mature. It typically takes about 10 years to get a working garbage collector that can be reliable and performs well. So it makes sense to have G1 as the default collector now. The other thing is that there are some more recent changes around G1. So concurrent class unloading was implemented in JDK 8 update 40, again was JET 156, and that was a good performance improvement for G1 that again made it more useful in terms of the default collector. One of the things you may notice is that because of the way the collector works, it's different to the parallel GC, and you may find that resource utilization is different. As I said, some garbage may not get collected on a particular cycle of the garbage collector, which means your heap size and the resident set may grow a bit more than you would have with the parallel collector. If that's a problem for you, then you can always switch back to using the parallel collector using explicit command line flags. The other change that's significant in terms of JDK 9 is that a number of the options that have been supported for garbage collection are being removed. They were deprecated in JDK 8 under JET 173, and these are really combinations of collection options which don't really make a lot of sense, or they're very old and they should really be retired. A lot of these take effort in terms of testing, and it doesn't make sense because who's going to use a parallel new collector with a serial old collector? It really doesn't make any sense. The other thing that is being sort of phased out is the idea of things like incremental concurrent mark sweep. That was something that was introduced to try and improve the performance of the concurrent mark sweep collector on machines that had a small number of cores or a small number of processors. So that's being phased out as well. So all these options are no longer going to be supported on JDK 9. If we look at a little bit further into the future, what's happening with garbage collection? What are people thinking about in terms of that? The answer is there's not really a lot going on. There's one big project that's still in the works, which is Shenandoah. Shenandoah is very much an experimental project aimed at producing an ultra-low pause collector. Now, as I say, it's experimental. It's part of the OpenJDK source code project. You can go to the OpenJDK pages. You can see what's going on. But it is most definitely not stable. It's not production ready yet. Certainly nobody would be using this in production if they are concerned about stability of their system. It's not scheduled for inclusion in OpenJDK in terms of a supported collector. So if you look at that, basically JDK 10, even JDK 11 has no idea of including this. It's still some way off from being a production-ready system. It uses the idea of concurrent compaction as well as concurrent marking. So it is a bit like G1, but it does the compaction concurrently with the application threads. The application threads are able to run at the same time that objects are being moved around. That might seem like a very strange thing to be able to do, but I'll show you how that can be done with Xing in a moment. This is targeted at very large heaps, greater than 20 gigabytes, so typically bigger than most people run on a reasonable number of machines. One of the interesting things about this is that they've decided not to go with a generational heap at the moment. They decided that they will keep the heap as a single region, and this does seem to be having an impact on overall performance. Most people use generational heaps because of a thing called the weak generational hypothesis. The idea is that most objects are very, very short-lived. If you can collect them in the young generation using the stack-based allocation and then simply ignoring the objects, that's a very efficient way of reclaiming that space. Once they get into the old generation and you have to do compaction, it becomes a lot harder in terms of performance. So by not having a generational heap, they are seeing some issues around getting the performance of Shenandoah to work the way they want it to. The other more recent thing is the idea of a NoOp collector, and this kind of goes back somewhat to what I was saying earlier on about people saying, well, the garbage collector is causing me problems. How about if I don't use the garbage collector? And this is a draft JEP that was submitted by Alexei Shipolev of Red Hat, and what he wants to do is create a collector that doesn't collect. The idea behind this is that it won't impose any overhead on an application. There's no non-deterministic behavior because it doesn't do any collection, so you won't see pauses when you're not expecting them. You also won't have unexpected length of pause. Problem is, of course, it's not going to reclaim any unused objects. So if you're generating garbage, if you're allocating objects and then no longer using them, this will not work for long. As soon as your heap fills up, you are dead in the water. You can't carry on. The other thing is it still needs to have the idea of allocation built into it. So even though it's a NoOp from the point of view of collection, it still has to be able to allocate objects, because the way that Java works is that you must be able to allocate objects. There are two places where this is theoretically useful. What Alexei is actually proposing this for is to be able to benchmark different garbage collection algorithms. So you use the NoOp collector, you run a simple algorithm, simple benchmark that doesn't generate any significant garbage, and that way you can see how your application code will run as a benchmark. Then you try different garbage collection algorithms and you see what the difference is, so you can see how efficient your garbage collection is. The only other place where this is applicable is where you might have a very rare situation where you really do have a zero garbage application. But as I said, it's not to be recommended to try and write applications like that for general purpose. Right, so what I'm going to do now is I'm going to run a poll question. Now, let's see if I can do this. So let's go to the poll and launch the poll. And what I want to do is I want to ask everybody who's listening to the webinar, how much do garbage collection pauses affect your Java application performance? And what I've done is I've put 5 options there. So do you find that garbage collection doesn't have any impact on your application performance at all? Are you really lucky that you don't have to worry about that particular side of things? Then second option is, okay, it is a bit of a problem, but we're able to easily tune around those, so we can change the way that the garbage collector works for our application, and we're able to see that the performance comes back into what we want. Do you spend a lot of time tuning your Java virtual machine and trying to get it to work the way you want it to and eliminating garbage collection issues? Or do you have a situation where it's a significant problem, where it is actually impacting your SLA and it really is causing you problems? And then I added a 5th option, which is where you don't know what a garbage collection pause is. So you're very lucky you've never seen a garbage collection pause, and so that's not a problem. Okay, so let's see. I'm going to close the poll now. Let's see what. Okay, most people have probably had a chance to respond by now, so let's close the poll and I'll just share the results of that. Okay, so it looks like most people are having a bit of a problem, but they're able to tune around it. But about a third of the people, because that's 30% of the people here are having either significant tuning issues or actually impacting on their SLAs. So that's interesting, because that was different to the results I had this morning on the one I did in Europe. I actually saw more people had significant time tuning their JVM and had effects on their application. Right, so let's hide the results here and go back to my application. Okay. Right, so let's move on. Right, so my question now is, what if we could solve garbage collection problems today? Let's not worry about the future. Let's not worry about what's changing in terms of the garbage collector in JDK 9 or JDK 10 or even JDK 11. What about if we could solve all of our garbage collection problems right now? So you didn't have to tune. You didn't have to add extra command line options or anything like that. And the answer is we can. And this is what Azul do. So Azul have a different way of approaching garbage collection. It's called the Continuous Concurrent Compacting Collector, or C4. Let's talk about this. How does this work? Well, what we do is we take the OpenJDK source code and we then remove all of the garbage collection as it's built in. So we take away CMS, we take away parallel collector, we take away the serial collector and so on, and we put in our own garbage collector. But we make sure that what we do passes all of the TCK, JCK tests. From the point of view of your application, it is simply a drop-in replacement. You don't have to change anything in terms of your code to run with the Xing JVM. It's exactly the same as any other compliant JVM. What we do then is we also work in conjunction with what we call the Xing system tools. It only works on Linux, and we support a very wide range of Linux distributions and revisions of different parts of Linux. But we need Xing system tools to make everything work. It also works across a very wide operating range. What we target this at is people who are interested in low latency applications. So we eliminate garbage collection pauses. But also, because you can make your heap space bigger, and you're not worried about the length of the garbage collection pause because we eliminate it, then you can have very big in-memory applications. We will scale all the way from 1 gigabyte of heap space up to 2 terabytes of heap space. So you can have some very big heaps, but without significant garbage collection pauses. In terms of allocation rates, we can keep up with what you need from 10 megabytes a second all the way up to 20 gigabytes a second. So if you've got you've got an application that needs a lot of objects created very quickly, we can keep up with that as well. How does C4 work? Like I say, it replaces all of the standard collectors you get in OpenJDK. It is a generational collector. So we have the concept of a young generation, we have the concept of an old generation. But we use the same algorithm for both regions. Why we have 2 different regions is, again, for efficiency. We understand the weak generational hypothesis, and the idea is that if we can eliminate most of the garbage in the young generation, then the old generation works more efficiently. It's still the same algorithm that's used, but because of the way that garbage tends to be generated in Java applications, having 2 regions in the heap makes a lot of sense. It is concurrent, which means we run the garbage collection threads at the same time as the application threads. It is parallel, so we run multiple threads to run the garbage collector at the same time as your application threads. And it is compacting, so we will compact the heap space as your application threads are running. The most important thing is that we do that without having the situation of a full compacting collection where we need to pause all of the application threads in order to do that. So there isn't this situation where at some point the garbage collector says, I can't keep up with everything, I'm going to now stop all of your application threads and compact the whole heap. It just doesn't happen. The way it works is using a mark, relocate, remap algorithm. So let me talk a bit more about that. First thing in terms of how that works is, how do we enable application threads to run at the same time as the garbage collector? Because, as I've said, if you start having application threads making changes to objects whilst you're doing garbage collection, you can have problems with inconsistency of your data. So what we do is we have a read barrier. Most garbage collection algorithms use a write barrier in terms of tracking the way that references are used. We introduce a read barrier, which means that every object reference that your application code uses will be tested to make sure that certain things are the way they should be. And what we do is we enforce two invariants on the way that the read barrier works. So every time you try and access an object, we will intercept the read of the object reference, and we will look at some bits in the object reference to see what phase of garbage collection we're in. If we're in a marking phase, we will guarantee that when you access an object, that object gets marked so that it's marked as being live data. You're referencing it from your application, so it must be a live object. When we're doing relocation and compaction, then if you try and reference an object, we will guarantee that the position that you get or the reference you get from that object pointer is the right one. So it will go to the right place where the object has been moved to. So you're getting consistency of data through this loaded value barrier, this read barrier. A lot of people say, well, okay, that's great, but doesn't that mean that you're now affecting performance? Because if you're intercepting every read of an object, surely that's a problem from a performance point of view. Well, what we are able to do with this is concurrent marking and relocation. From a performance perspective, all we're doing is two things. We're doing a test and jump, and that's two instructions that we need to do. We look at the bits in the object pointer, and we say, is the state what we expect it to be? If it's not, we need to jump to a trap handler and do some work. If it is, then we carry on and we don't need to do anything else. On an x86 architecture, this boils down to essentially 1 micro-op. So it's a very, very low overhead in terms of your application. We've done a lot of analysis of this. We've done a lot of benchmarking. And what we've found is that the only time you would see any impact on the performance compared with not using a read barrier is where you were literally only ever using data from your L1 cache. As soon as you go to L2, L3, or main memory, the effect of the loaded value barrier is so small that it'll get lost as noise compared to what you're doing in terms of accessing the different caches or the main memory. So very few applications would actually only work in L1 cache. Even then, the performance impact is somewhere in the region of 0.5 to 5%, only if you're using L1 cache. How does this work? Right, so we have the concurrent marking phase. What happens here is that we start marking. Same idea as we have with concurrent mark sweep or mark sweep compact. What we need to do is mark all of the objects which are still live data. So the garbage collection will start and it will create this root set. It will look at all the references we have from the stacks associated with our application threads. It will look at all the references we have from the current registers, and it will create a root set. That root set will give us a list of objects, and what we need the garbage collector to do is to then mark each of those objects, but then to follow the links that that object has to other objects. It will then mark those objects as being live and continue to do that, tracing the whole graph of referenceable objects from the first element of our root set. Because we do this in parallel, we'll have multiple threads that will enable us to work on the root set and mark objects, references in parallel, so we can process things very quickly. The application threads are running at the same time, so they're running concurrently. Let's say our application thread comes along and says it wants to access an object. This object is not in our root set. Even if it was, we don't care, but we are able to access that. So the application thread will then make a reference to that object, and then we'll get the object reference from the JVM. As it does that, it will hit our read barrier, and the read barrier will say, we're in a marking phase, this object hasn't been marked. So the application thread will then mark that object as being used. So it becomes a used object. We know it's being referenced, so it gets marked. That's the first invariant that I mentioned earlier. What it also does is it then says, okay, well, we don't want to bother doing all the work of tracing this object's graph, so we will then move that to the root set of the garbage collector, so that the garbage collector at some point will find this object and will then trace all of the other references from it. But we know that this object that we're now accessing is one that we are using. The next time we come through, if let's say we're in a loop and we're accessing the same object again and again, the second time and subsequent times that it comes through, it's going to hit that read barrier, but the test will fail and it won't, or will succeed, and it won't bother going through the trap handler, and it won't have to do any extra work. For the relocation phase, what we do is we say, okay, we've got garbage and we've got live data spread around our heap space. We'll treat these as pages of memory, and we'll relocate our objects. We'll work out where those objects need to be copied to. So we can see that we can move our objects into different pages, and we can effectively compact our data. What we also do at that point is we create a table separate from the heap space, which is our translation table. Now, other algorithms tend to use a forwarding pointer that's in the object reference itself, but we don't do that. We use a side table to do that, and there's a very good reason for that, which is that because we're able to work with the Xing system tools, we have control over physical and virtual memory. So we actually work with the memory system. If you think about the way that memory works, you have a virtual page which maps to a physical page of memory. And so all of the pages that have live data in them have a physical page associated with them. When we want to do collection, we need a physical page to back our virtual page that we're going to compact into. So we take one page and we compact our data into that page. For the next page, we need another physical page to back that virtual page. But rather than taking one from wherever, we actually reuse the one that we've just taken the data from. Now, we're able to do that because we know that none of the data in that virtual page is ever going to be used again. That's the reason for having the separate table with the address translations, rather than keeping them in the address, in the object pointer. So we're able to disassociate that physical page from the virtual page and reuse it. So then we can continue our compaction, and then if we need another page later on, let's say we're allocating some new objects, then we're able to reuse a physical page again that we've just done compaction from, and we'll take advantage of the fact that these may well be in cache, and we get better performance from that. The remapping phase is where we need the garbage collector to then go through and use that table to modify the values associated with the object references. So it goes back and looks at all the object pointers and says, right, we need to change that to point at the new position of the object. Application threads are running concurrently. When we hit an object that hasn't been remapped, then obviously the trap handler will be called because the bit isn't set. And so at that point, the application thread will go through it, will find the reference, it will change the reference so that it's got the correct one, and update the bit to show that it has been remapped. So the next time it comes through, we don't need to do that again. Talk very briefly about GC tuning. Now, GC tuning tends to be quite an art form and very difficult to get it right. Lots and lots of options that we've seen to do that. And so those of you who are already familiar with garbage collection tuning know about all these different options. And this is the kind of thing you see. So these are two real-world applications, the command line to start up these applications. Lots and lots of complicated options, not necessarily well documented, difficult to know which to use with which. And just to highlight one thing here, what we've got is a survivor ratio at the top of 128, survivor ratio at the bottom of 2. Now, how do you know which one to make it? Do you make it 2? Do you make it 128? Very difficult to predict that based on what your application is doing. So tuning is a really difficult thing for other types of garbage collector. For Xing, it's very simple. We don't have any of that. All we do is we set the size of the heap. So we say Java -XMX 1 GB, or 10 gigabytes, or 100 gigabytes, or 2 terabytes. That's it. That's all your tuning is done. So you simply set the size of your heap and it's over. Now, just talk briefly about analyzing performance, because I've got a couple of minutes left. One of the problems of analyzing performance is knowing whether it's the application that's causing the problems of your performance, or is it the JVM, or is it the operating system? JVM does a lot of work for you, so it's difficult to understand where you might want to apply tuning. Do you tune your application code? Do you tune your JVM? What's actually causing you the problem? So to help with that, we've created a thing called Jhookup. And Jhookup is designed to measure the impact on your application of everything below your application, JVM, operating system, hardware. It is designed to be very non-intrusive, so it doesn't actually interact with your code at all. It runs in a separate thread alongside your application within the same JVM. So it experiences the same effects as your application, but in a separate thread. All it does, most of the time, is sleep. So it sleeps for 1 millisecond, wakes up, it does a little bit more than that, but it sleeps for 1 millisecond, wakes up, and says, how long is it since I thought I was going to wake up to when I actually woke up? If you had a garbage collection pause that had kicked in whilst it was asleep, the time that it woke up would be a lot later than it was expecting to wake up. What we can then do is create histograms and graph those to show where the hiccups are happening with your application. Not the application code, this is everything below it. So we can see a graph here where we're seeing spikes in our latency, which are probably garbage collection happening. And then we can also graph that by percentile so that we can see in terms of our SLAs whether we're matching the latency we need within a given percentile. Just to kind of put that into context, this is a Hazelcast benchmark that we did. So you can see on the left-hand side we're running hotspot JVM, and what we've got there is fairly consistent pauses somewhere in the region of 20 to 40 milliseconds with a spike at the beginning up to 230 milliseconds. On the right, we're seeing Xing, and very, very flat. You're probably getting somewhere in the region of 4 milliseconds of distortion for your application. Same thing for a solar benchmark. This is running on 16 gigabyte heap, looking at G1 versus Xing. Again, G1, even with the ideas of improving performance, still seeing some very significant pauses here, like 250 milliseconds, fairly average, all the way up to 1.5 seconds. Xing, flatline. It's well below 100 milliseconds by the looks of things there. So just to summarize, because I'm just about out of time, garbage collection is a very powerful feature of Java, but can cause problems because it's non-deterministic. G1 does make things better, but it still has to fall back to a stop-the-world collection. Shenandoah is another idea, definitely not production ready. Xing solves the problem of garbage collection. No more garbage collection pauses like you're seeing at the moment. Focus on the application, not the infrastructure. Focus on solving the problems that you have in your business logic, rather than trying to tune the JVM. We're also working on other things around Xing to improve performance of things like the JIT compiler, warm-up of the JIT compiler and things like that, which I will talk about in another webinar. If you're interested in using Xing, you can get a free 30-day evaluation license. So if you go to info.azul.com, Xing trial, then you can download the necessary license from there and you can try it out. As I say, it's a drop-in replacement. You simply download it, set it up, change your Java home, off you go. So with that, I'm just going to see whether we have any questions. So let's have a look. Questions. There we go. Oh, I see no questions. Oh, there we go. Can we get a soft copy of your slide? Yes, the slides will be made available after the presentation. You'll get a link to both the slides themselves and also a recording of the presentation. So that will be sent out shortly in the next couple of days. So yes, I will definitely make those available. I don't see any other questions. So I'm guessing since we're just on the hour, yes, just after the hour. So thank you very much.